techniques that we can use to modify expressions and integrals such that when they are not originally integrable by the techniques that we've learned or the formulas that we know, we can use these techniques. So we were talking about trig identities. So this is the first of many cases where we're going to use trig identities or try to use trig identities to rewrite the integrand, this part of the integral, such that it is something we can integrate. So right now we don't have anything, if we had just a secant of x by itself or 1 by itself in the numerator, we could integrate this thing, but it's in the denominator, so it's not anything we've seen before. So if you see situations where you have the sine of x plus 1 or the sine of x minus 1 or the cosine of x, any trig function plus or minus 1, you might be able to do this technique. So what we do is we're going to multiply the numerator and the denominator by the Pythagorean conjugate. And we've heard of conjugates before when it comes to the complex number system, complex conjugate. But I guess the more general definition is it's some grouping of terms where you change the sign of one of them. You duplicate it except you change the sign of one of them so that the inside and outside parts of the FOIL calculation disappear. So if we do, in this case, the numerator is going to stay the same for right now. And then the denominator, when we multiply out this original term multiplied by its complex conjugate, and you get secant squared x minus 1, because you get a plus secant x and a minus secant x, which cancel out, and you just have the first terms multiplied together and the last terms multiplied together. And then you go over here and look for one of those Pythagorean identities. And I always remember that just the first one. If I forget the other ones, this one's used so often that you get used to it. So if you start with that, and what I'm looking for is something involving the secant. So what I would do is divide everything by the cosine squared, because I know they got 1 over the cosine is the secant. So the first term, using the quotient identity, becomes a tangent squared. Cosine over cosine is 1, and 1 over the cosine is the secant. So if we subtract 1 from both sides, we get tangent squared of x equals 1, or secant squared minus 1. So then I can make that substitution over here. I'm going to go ahead and factor out the 2/3. Okay, so we've got secant x plus 1 divided by tangent squared x dx. And now what you can do is you can break that up into 2 fractions. So we get secant x over tangent squared x plus 1 over tangent squared x, the whole thing times dx. But let's just look at this term, secant x divided by the tangent squared. Well, the tangent, let's write this up. It's tangent squared x. So the secant is 1 over the cosine. The tangent is the sine over the cosine, so we get sine squared over cosine squared for tangent squared. And then you would take the reciprocal of this, which would be cosine squared over sine squared. So once you cancel this out with one of those, you end up with cosine x divided by sine squared x. Is that right? Okay, dA. Well, so now let's plug that in there. So we got two integrals. We got the integral of cosine of x dx. I'm going to break it into two separate integrals. Sine squared x plus 2/3. If we take the reciprocal of the tangent, we'll get the cotangent squared of x dx. Now, the way you solve this problem is you let u equal the sine of x. And over here, what you have to do is actually rewrite using the, there's the other Pythagorean identity, which is going to be, if we divide these by the sine, so if we had sine over sine, you'd have 1. Cosine over sine is cotangent, and 1 over sine is cosecant. So what we have to do in this case is rewrite that as, so cotangent would be cosecant squared minus 1. And over here, you'd say the sine of x is, u is the sine of x, so the du is the cosine of x dx. So with that substitution, you would have the integral of 1 over u squared du. Yeah, this was longer than I remembered it, but I'm pretty sure I'm doing it right. And you're like, but don't worry, I'm not going to put this on the test. But just to give you an idea of the procedure, I didn't say it was going to be easy, but it works. And then we rewrite 1 over u squared is u to the minus 2 power. I'm just going to follow that down. Now I'm going to integrate. So you get 2/3 times u to the minus 1 power divided by negative 1. Over here, you get 2/3. The integral of the cosecant squared is one that's in the book, and that's equal to negative the cotangent of x. So the integral of cosecant squared is negative cotangent x. The integral of negative 1 is negative x, and I should have taken the integral signs off of here because I'm integrating. So the integral of the cosecant squared is negative the cotangent of x, and the integral of negative 1 is x. And then you'd add your arbitrary constant c, and finally you'd plug u back in, and u was the sine of x. So this negative comes here. If I put the sine of x in to the minus 1 power, it's the same as 1 over the sine of x. Then I have 2/3 times negative the cotangent of x minus x plus c. And finally, you'd write that as the cosecant. So you'd have negative 2/3 cosecant of x plus 2/3 times negative the cotangent of x minus x plus c. Ta-da! Amazing, huh? Hopefully I did that right. But yeah, I mean, so we start off with this thing that we couldn't solve, and we went through and we used the Pythagorean conjugate to create something in the denominator that I could use one of the Pythagorean identities to replace with one term, which is what I did there. Then I broke it up into two fractions, and I rewrote this so that it wasn't a fraction anymore. Then I looked at it and said, oh, that's still not integrable, but I do remember that the cosecant squared is integrable, so we'll make that. We'll use another Pythagorean identity. And over here, you know, when I rewrote these in terms of sine and cosines, I was able to fit it into something that I recognized. Once I saw cosine x dx and I saw it was divided by the sine, I thought, oh, I'm in good shape. I can do that. So that, you know, again, these are things you wouldn't immediately recognize at this point, but after you do quite a few, you do kind of pick up on them. And it does give you an answer, which is kind of interesting because it's a crazy result, right? It's got three parts. Some of it's Some of it's trig function, some of it's polynomial function, but it works. If you took this original curve, whatever the heck this thing looks like, and you wanted to find the area underneath this curve between 2 points, you could use this and as a definite integral, and you could find the area underneath the curve. Okay, so that reminds me, something turned out more difficult than I expected. So yesterday I decided to try what I asked you to do for the assignment, which was to calculate those 4 integrals on the sheet, and I recorded it, and it took me about a half hour to do the first one. Yeah. I tried to do it all in fractions, but you end up with a denominator of 10,000 something. So it gets pretty crazy with the denominator. So I'm going to still ask you to do it, but you don't have to deal with fractions, okay? Just once you do the integral, I would do the integral with fractions, but once you plug in the numbers, and part of the reason it was such a pain was because I had in one of the limits was 27/5, which by the time you take that to the whatever it was, like 4th power, 27 to the 4th power becomes a huge number. And then so the amazing thing was that I got it right. If you want, well, I don't know if I'll post the video or not, but I got it to the end and it was like this one. I'm like, woohoo, I did it. I might even show it to you just because it's interesting. And I just realized I forgot to push no, it's recording. Okay. I didn't see my little, oh, there they are. Okay, good. Let me just open up my thing here. I think I saved it. It's just a warning, word of warning. I think it's still worth doing, but it is trying to do it as fractions. I gave up on it. So maybe was it this one? Yeah, that was it. Okay, so this was the, I'll just show you how it worked out. Okay, so here's my integral. Pi times the integral of 3/2 to 11/3, and from 11/3 to 27/5. And let me minimize this thing. So what I did was well, originally it was this equation. So it started with this equation. Then I multiplied these things out to get that equation. Then I factored out a 9 in the denominator, so I ended up without any fractions. And ultimately ended up with the integral like this, the integral of 9x squared plus 18x. Well, then I had to combine the two. So I combined the x terms. 9x squared minus 1x gives me 8x squared. So I had the two integrals, and then I integrated them. So I ended up with something like, here's 35x cubed over 3, evaluated at 27/5. So then you stick all that stuff in there. So there's all the fractions. I haven't actually evaluated them yet. And then, yeah, that's the page that I started to reevaluate my my decision to try to get you guys to do this, because if you come up with the common denominator from all these numbers, it's a big number. And you can see I've got 301,806 50ths. At that point, I was wondering whether I was making a mistake or whatever. So I got all the way to the end. Oh, and here I combined these. I found the common denominator for these three and these three and these three. And so, by the time I got it all together, I had like 1,771,470 750ths. So there's my answer. I went online, put the equation in. I got 98.71. So what I'm telling you guys is, when you get to this point, plug that into your calculator. Don't try to do it as fractions. That'll save you at least half the amount of time to do the problems. But I do want you to get to this point, because all you're doing is you're taking your equation that you got from integrating and you're plugging in the fractions. And I think that's reasonable to do for you guys, but leaving it entirely in terms of fractions, it was just too crazy. Okay, so that's that one. Let's see if I got the answer right here. Yeah, it looks like it. Or is that my answer I just got? Anyway, we'll assume it's right. Okay, so that was one example using the Pythagorean conjugate. The next thing is it's called add and subtract terms in the numerator. So what I've got is an integral of a rational function, and your first thought, if you don't have anything in parentheses or square roots or anything like that, would be to choose the entire denominator as u. So let's just do that and see what happens. So let me add a page. Also, I'm going to turn this. It's funny, even though the speakers are off, I can always hear this thing a little bit when I touch my tablet. So I have to turn it on and then turn it off, and then I don't hear it. I haven't figured that one out. Okay, so if I let u equal the entire denominator, and I take the derivative, I'll get 4x plus 3. Now you can see what I have is 4x, but I need 4x plus 3 to be able to make this du over u. So what I do is I take 4x and I add 3. And then I have to subtract 3 like I normally do. So I would subtract 3 divided by the same denominator. So I've added 3 over 2x squared plus 3x plus 9. I've subtracted 3 over 2x squared plus 9x plus 9. So I've just added and subtracted the same thing. So here you would let u equal 2x squared plus 3x plus 9, and du would be equal to 4x plus 3 whole thing times dx. So when I integrate this, I'd end up with the natural log of the absolute value of 2x squared plus 3x plus 9. Because this becomes the integral of du over u, which is equal to the natural log of the absolute value u. So that's how I get that part. Now here, what I would have to do is it would be an arctangent result. Now it's not in a form that looks easy right now to deal with, and I don't know why I chose. This denominator is more complicated than it probably should be. So I'm not actually going to solve this at this point, but what you would have to do is you'd have to use completing the square to create. Well, I can do it. It's a little tricky, but it's not. What I would do is I would create a situation where I have 1 over a squared plus u squared, which is an integral that's in the book. I could have chosen an easier one to do, but I'll demonstrate it anyway. So what you do is you take this denominator, and we would factor out the 2. So you'd have 2 times x squared plus 9 halves x, and we add our 9. So all I've done is put some parentheses in there. Then I would take 9 halves, and I'd divide that by 2, and I'd square it. So you take this number and divide by 2. So that's 81 over 8. So sorry, it's oh well, yeah, because I'm dividing by 2, so it's 3 half. It's going to be 9/4, right? I'm dividing by 2 here. Oh, I wrote it wrong down. You're right. Sorry. I see what you're saying. Thank you. because I wrote the wrong number down. Okay, let's fix that. Okay, so you factor out the 2, so you get 3 halves. So what we do is we take 3 halves, divide by 2, square that. So that's 3/4 squared, which is 9/16. So I add 9/16. And I have, because I'm adding 9/16, but I'm really adding 18/16, so I'm going to subtract 18/16 to compensate for this adding 18/16. I know I can simplify that, but so you would get 2 times x plus 3/4 squared, and here we'd have, okay, that'd be 9/8, and this would be 72/8. So you subtract that, you get 63/8 plus 63/8. And so that's what you could substitute for, and you would, and the integral that we're trying to fit it into is 1 over a squared plus u squared, and the result in du is equal to 1 over a times the arc tangent of u over a plus c. So a would be the square root of this thing. I forgot about, what did I do with the 2? Anyway, let's not worry about the details, but that's the basic concept. So I probably, that was it. So there's your homework problems. What I'm going to do is I'm going to find a better problem. I don't know why I had that in there. I would have thought I'd realized it by now. That one's harder than it needs to be, so I'm going to find an easier one to demonstrate it again to you. So I made the test up, so it's ready to go. The review is fairly short, so I don't go into a huge amount of detail, but I do tell you what kind of problems to expect. I think I have on the next page just a couple where just some hints. So, for example, this one, you probably would use the Pythagorean conjugate to do that because it's cosine theta minus 1. So I'd multiply it by cosine theta plus 1 in both the numerator and denominator. This one looks a little tricky, but it's actually, if you take it and break it up into 2 parts, you'll have 1 over x minus the natural log of x over x. And in this case, you let u equal the natural log of x, and therefore du is equal to 1 over x dx. So that's kind of how that one works. Sometimes, a lot of times we haven't had anything in the denominator when it comes to these du terms, but because of the natural log here and the fact the derivative of the natural log is 1 over x, it does work out. What else have we got? Oh, here's some more hints. In here, what you would do is, this is number 8. This is a term in the parentheses, and so you'd let u equal this, and you'd let a equal that, a squared equal that. So this is u squared plus a squared. So this is an arctangent problem. This one's just a normal u substitution because you've got the derivative of the argument of the square root is the numerator. So that one's pretty straightforward. Just looking at some of these other ones. Yeah, like this one, 13, you got the cosine of x times e to the sine of x. Well, you let u equal the sine of x. The derivative of the sine is the cosine of x. So you get cosine x dx. Here you'd let the whole thing be u. You probably, and you'll, here you'd let the whole denominator be u. So the derivative of this is that. Okay, we're going to move on here. We're not learning anything real new in section 1. We're just kind of redoing stuff we've already done. Okay, so the next topic is integration by parts. And this first page is just telling you what we know and what we don't know. We do know that the integral of, no, we don't know that. Oh, no, yeah, we do. The derivative of the natural log is 1 over x. And I don't know why I have the c in there. That's ridiculous. Okay. So the derivative of the natural log of x is 1 over x. The integral of 1 over x dx is the natural log of x, the natural log of the absolute value of x plus c. The one we don't know, which I've marked out here, is what is the integral of the natural log of x? So you think we've done everything involving the natural log of x, and yeah, we know how to take the derivative of the natural log of x. We know that the integral of 1 over x dx is the natural log of x, but we don't know how to do the integral of the natural log of x. And integration by parts is one way to handle that. There are a lot of others, situations. And integration by parts addresses integrals of the forms shown here. So it'll do the integral of the natural log of x. It'll also do the integral of x times the natural log of x. If you have the integral of x squared e to the x dx, notice that if it was e to the x cubed, I could say u is x cubed, and the derivative would be 3x squared. But in this case, I just have e to the x in the numerator. So we can do that one with integration by parts. We can also do e to the x times the sine of x, which is a product of two things we know how to do individually, but not how to do them as a product. And like I said, the one natural. A lot of times, most of the time, they involve products of two terms. But there are a few special cases like the last one where it doesn't involve a product. It does actually. It's the product of the natural log of x and dx, but that'll become more obvious. So here's the derivation of the formula, how it works. So it's kind of like integrating factor. What we're going to do is we're going to take advantage of the product rule, but in a different format. So the product rule says that the derivative with respect to x of a product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first function. And just like we did with integration by parts, we're going to simplify the notation. So we're going to let f of x just be represented by the variable u, and g of x, the second function, represented by v. We kind of did that in integration by parts by using u and f and g and that kind of stuff. So the product rule in terms of u and v becomes this. The derivative with respect to x of u times v is equal to u times the derivative of v with respect to x plus v times the derivative of u with respect to x. Okay. Now what do we do? We're going to go even a little step further. We're going to use a slightly different notation. So instead of taking d dx, we're going to put the prime. We saw that notation in integration by parts. So u times v prime. And then you can write this as u times v prime. This is v times u prime. So the prime means just the derivative with respect to x. Again, it's just a little bit easier way of doing the notation to derive this. We haven't done anything except change the notation up at this point. So we multiply every term by dx. So we can do that because it's algebra. So we end up with that. Whoops, what happened there? Okay, let's keep going down here. So we multiply everything by dx, so we get that. And then we integrate everything. So we get the integral of uv, quantity uv prime dx, the integral of uv prime dx, and the integral of vu prime dx. Now, like with integration by parts, we had the same kind of situation. So if you integrate something, a product of a derivative of a product, integrate the derivative of a product, you just get u times v. So the left-hand side just becomes u times v. And what we're going to do is we're going to combine these two. V prime is dv dx, and then we're going to multiply by dx. So the dx's are going to cancel out ultimately. So what we're doing here is we're saying that v prime, we're going back to the old notation. So we switched the new notation to do a little bit of manipulation, but now we're going to switch back to the old notation for a second. So v prime is dv dx, and then if you multiply dv dx by dx, you end up just getting, this just becomes dv, and likewise over here, du dx times dx becomes du. So v prime is dv dx, but if we take v prime times dx, we get v prime times dx becomes dv, and u prime dx becomes du. And so I'm going to write this out instead of just unveiling stuff here. So the first one, based on what we saw with integration by parts, just becomes the product of u and v. The second term becomes the integral of u dv. This term becomes u dv. And the third term becomes v du. And if we rearrange the terms, so I'm going to solve for this, solve for this. So what we would get the integral of u dv is equal to u times v minus the integral of v du. Okay, so that is the formula that we're going to use. So we're going to take our original integral that we don't know how to solve, which consists of two parts. One part that we call u, and one part that we call dv. Once we make that identification, we know the answer is going to be u times v, and v here will be the integral of this part. The v is going to be the integral of dv. That's how we get v. And then we also get v. We plug v in here, and then we multiply by du. Okay, you'll see it once I work an example what it all means. Okay, so let me just show you an example what this all means, and then we'll tell you how to choose. The next thing is how do you choose what's u and what's v. So if I wanted to know what the integral of x times e to the x dx is, I know what the integral of x is. It's x squared over 2. I know what the integral of e to the x is. It's e to the x. But I've got this product that's not going to fit in anything that I currently know. You know, if this were x squared, then I let u equal x squared, and this would become, you know, e to the u. This part would be du over 2 or something like that. But it's not going to work using our normal techniques. So what we're going to do is this is the integral of u dv. but it doesn't tell us which is u and which is v. So I'm gonna make a choice and show you how it works, and then I'll explain why I made the choice. So I'm gonna let u equal x. So that's the u part. And the rest of it has to be dv by default. So dv is e to the x dx. So this becomes the integral of u dv. Now, I have to calculate a du because I need that here, and I need to calculate a v because I need that there, but it's not that hard. You take your original u selection, you take the derivative, just like we normally do when we're using u substitution. So the derivative of x is 1, and then we multiply by dx. So same usual u substitution kind of situation. Now v is the integral of dv. So I didn't write that down over here, but I said it. dv is the integral of dv. So in this case, dv is e to the x dx. So I know how to integrate that. The integral of e to the x dx, it's in the book, is e to the x. Now I don't add an arbitrary constant c here, I just leave it without an arbitrary constant c. So once I have chosen a u and let the rest of it be dv, I calculate du the normal way. I calculate v by integrating it. And the key thing here is that my dv is such that I can integrate it. I couldn't integrate the product, but I can integrate part of it. So that's my v. So I have all this now. I look at my integration by parts equation. And so, this is the integral of u, which is the x part, and dv, which is the red part, okay? And based upon just taking the product rule and manipulating it a little bit, I know that the integral of x e to the x dx, which is this side, is equal to u. U is x. V is e to the x. And then I subtract the integral of v, which is e to the x, times du, which is just dx. And then, hopefully, I can integrate this now. Hopefully that second integral that I used here is integrable. This one wasn't integrable by itself, but this one is. So the first term just becomes, you bring that down, and the integral of e to the x is just e to the x. And then you add your arbitrary constant c at that point. So it says the integral of x e to the x dx is x e to the x minus e to the x plus c. And that's your answer. Okay, so that's the basic concept of integration by parts. And it involves initially an integral that I don't have any result for in my table. It doesn't automatically, by going through this process, you don't just plug numbers and get the result. You have this second integral that you have to deal with. But if you choose u and dv appropriately, this integral will be solvable, or we'll be able to do something with it. And if I take the derivative of this, the derivative of the integral should be the original term. If I take the derivative of this, you'll see that it ends up working out. Skip all that stuff. Okay, that's another example. We'll come back to that in a second. So here's the procedure. So the first thing you do is you start with some integral that you don't know how to solve, and it's a lot of times is a product. So you start with an integral, and you identify part of that integral as u and part as dv. The dv always includes the dx part at the end. Okay. Now dv is usually the most complicated part that fits a basic integration rule. So you can see I've got the same problem over here. both of these fit an integration rule. I know how to integrate x, and I know how to integrate e to the x. But dv is usually the most complicated part. So of these two choices, this is the most complicated part because it's not a polynomial. So that's why we choose this part to go into the dv part. Whereas the u part is usually a function whose derivative is simpler than the original function. So let's look at both of these. Let's look at this example. Let's look at x. So x is integrable. Integrable, but it isn't the simplest. I mean, the most complicated. Isn't the most complicated. E to the x is also integrable, but however, is the most complicated. Okay. So based upon this kind of rule, I would probably choose e to the x to go with the dv part. But there's also the fact that x, the derivative of x is 1, which is simpler. What does simpler mean? Well, if I had, let me just draw kind of a hierarchy of simpleness, okay? So here's simple, and here's difficult in terms of functions. So the simplest would probably be 0, okay? Then you'd have maybe a constant. Then you'd have x. Then you'd have x squared, x cubed, you know. So the more exponents you have on a polynomial, the more complicated it is. So most of the time, if you have a polynomial, whether it's x or x squared or x cubed, that's usually, not always, but it's usually the u part of the integral. Then when you get to things like probably the natural log of x is probably the next one once you've gone through all the polynomials, and then you'd probably have e to the x, and then finally maybe the sine of x, cosine of x. Those are all equally difficult. Why is that the case? Because if you look at the derivatives, so these are the original functions. If I look at the derivatives, so I don't have enough space here. I need to move everything down a little bit. So another thing about simpleness is this is f of x, and this is f prime of x. So the derivative of 0 is 0. The derivative of constant is 0. The derivative of x is 1. The derivative of x squared is 2x, so forth and so on. The derivative of the natural log of x is 1 over x. So you go from this is a rational function. This is a transcendental function. So it's becoming more simple. I might change the order here. These might be flipped. The derivative of e to the x is e to the x. So no, I think I'll leave it that way because here you're basically the same level of difficulty. E to the x, e to the x, they're the same function, so there's no change. You're not getting any simpler. Here we are getting a little simpler. The derivative of the sine is the cosine. That's equivalent. You usually don't get worse, but so you can see all of these, when you take the derivative, become simpler. They move down the chain as far as the simpleness chain. These tend to be the next ones, and then the trig functions are the last ones. So the derivative of x is 1, which is simpler than the original function x, whereas whereas the derivative of e to the x is e to the x, which is the same, hence not simpler. So I don't think that's the right spelling, simpler. Anyway, so that's the basic concept here, is you take your original expression, look at them. U is the part of the function whose integral is, whose derivative is simpler than the original function. The dv is the most difficult function that I can integrate using the tables. Okay, so we'll continue on with that next time.